Thank you very much, Paulo, for the very nice introduction, and thank you all for the invitation and for being here. So I have a disclosure just already from the beginning. So I didn't know much, who was going to be in the talk. Nowadays, with online talks, you have, many people that already know everything you're going to talk about, and many people that don't know anything you're going to talk about. So I tried to do a presentation that, at some point, if you're an expert, you're going to be bored. If you're not, you're going to maybe like it. And then at some point, I'm going to, move to proof theory and put like rules and blah, blah, blah. And then maybe you're going to say, now I got the point. And if you're not an expert on that, you're going to be bored. So just to let you know that the presentation is going to vary from time to time. You feel free to stop me at any point and interrupt me and ask questions, and we can have a very nice conversations. I put here 44 slides, but don't worry. I mean, we're going to skip some and talk about things that we think it's more important. If we have to stop at some point, we stop at this point and discuss this point, okay? So it's a pleasure to be in the Luci. I like it, the name a lot. My name, my mother's name is Lucia, so it's something that and Luci is such a bright kind of name, right? I love it, and that's why I put the logo here. The logo is fantastic as well. So this is what I'm going to talk about. I'm going to talk about ecumenical systems. So I'm going to explain to you what I mean by that. And I'm going to start with natural deduction, okay? So, and this is a brand new, this part of natural deduction is a brand new work that we've been doing together with Luis Carlos. And when I talk about modalities, then the work is going to be also with Luis Carlos, but also with Sonia and Emerson, okay? So let me give you two motivations. So when we teach logic, right, in the basic course, and then we talk about classical logic, and then we move to intuitionistic logic, you may do the other way around as well. But, normally this is the, standard example that you put, that you show to your students to show to them the difference between what's classical thinking and what's intuitionistic thinking. So if you take this theorem in mathematics that says that there are two irrational numbers such that one to the other is rational. So this is a theorem in mathematics, and then you prove this theorem, and the proof is really simple. You can consider square of 2 to the square of 2, and then you have two possibilities classically, right? Either this is a rational number or it's not, right? So if it is a rational number, then you're done, because you have square root of 2 is irrational, and then you have a rational number to the same irrational number, and you're going to have a rational number at the end if this is rational. If it is not this case, so if A is irrational, then you take A as X and you take Y as square of 2, and then you're done the same, because you put one to the other, you're going to have 2 at the end. So it doesn't matter if this number here is rational or irrational, you can prove this theorem, right? You can find witnesses that are going to tell you that this theorem is proved. It is really a theorem, right? Okay, but the question is, so if you're a classical mathematician, you're going to be fine with that. It's okay, right? But the question is, and if you're not a classical mathematician, and if for you to have a proof of something, you really have to tell me which one is the case. Is this a rational or irrational number, okay? So then an intuitionistic mathematician is not going to be happy about it. For him to be happy about this proof, he would have to show a proof that this number is either rational or irrational. Okay, so this is the Hilbert's 7 problem, actually, to prove that, well, more than that, right? It's not, this is, how can I say that, instantiation of the problem. So I'm not going through this really slowly, because, otherwise we don't get to the point quickly. But the only thing, the thing is that if you prove the Hilbert 7 problem, and it is written here, if you take two algebraic numbers such that the base is not it's not 0 or 1, and if beta is not a real rational number, then one to the other is transcendental, is more than irrational, is transcendental. So the case that we had before is a special case of this one, when you have alpha and beta square of 2. Okay, they are not rational, neither of them, and they are algebraic numbers, right? So okay, so now we are set, because if this problem, I mean the Hilbert 7 problem, is proven, and then we know that square root of 2 to the square root of 2 is irrational. Okay, it's transcendental more than that. Yeah, then you go and the proof is like this, and then you conclude the proof, and there is an oops at the end of the proof that would be that the proof is by contradiction, right? So it's not really, it's not a constructive proof this time, but okay, great. So so this is the difference between the thinking in mathematically classical or intuitionistic. Okay, so what we're going to do here is exactly to come back to this discussion, and you can say, "Whoa, I mean, this discussion has been there forever." And is there anything new to talk about it, right? Yeah, actually, we think there is. And the fun thing about this whole project, I must confess to you, that would be to be able to revisit many works that I read a long time ago, and now I could read again. So, for example, Marcello's work on classical natural deduction. And many other works that I read, long ago, but now they make sense to me in a better way. So the term ecumenical that we're going to use here we are going to use this word for unicity of views, of ideas, of ways of reasoning. So this is the way they're going to use this term ecumenical. So we're going to be based on Prawitz's vision of ecumenism, although he didn't coin this word. It was actually Luis Carlos that did that. And what I'm going to do today is really to talk a little bit about what are ecumenical systems in this setting, Prawitz setting. What are they good for? Why we should be interested in that, and what's the real motivation behind the definition of ecumenical systems, okay? And we're going to do that really slowly, so starting from natural deduction, then passing through sequent calculus, and then going to modalities. The modalities part, I'm going to do it really quickly, because it's really too technical, and I don't want to be really technical in this talk. So Prawitz, so in his vision, so his question was, what makes a connective classical or intuitionistic, right? So this is the question we're going to try to answer, also to modalities. Great. His main motivation for that was a philosophical motivation. There is, in philosophy, I think that most people call this inferentialism. But it's also in some sense is also proof theoretic semantics, and the idea is to try to find the meaning of logical constants by the rules of a system. Okay, but for being able to do so, you need to have a good proof systems. So as Marcello puts very well in his paper, when you talk about the logic, you can talk about validity, blah, 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 but you talk also about the systems, right? And you can have the same notion of consequence relation. But then if the system is different, then you have a whole new logic, right? A whole new system and a whole new way of looking at the system, whole new interpretation. So that in this sense, we can call this a semantics, right? Only looking at the rules of the system. And for that, the system has to be good, has to have good properties. So for example, harmony and separability, purity. I'm going to talk about these things during the talk. So one thing that is for classical logic in natural deduction, I'm going to start with natural deduction. One problematic point is exactly harmony, okay? I'm going to say exactly what I mean by that. And pure logical systems, they are good in the sense that you don't define connectives based on other connectives, okay? So this is the other thing we're going to try to do the same as well. Well, here I put, so this is a whole philosophical motivation. I put here a logical motivation given by Luis Carlos. He has this very nice dialogue between an intuitionistic logician and a classical logician. And this is the spirit of what Prawitz means about, you know, his ecumenism. That's going to be clear in a sentence that we're going to put later on. So imagine that the intuitionistic logician talking to the classical logician says, well, if you mean A or B, if by A or B you mean not A and not B, then I can accept that A or not A is valid, okay? But then the classical logician says, wait a minute. I mean, I do not want to have, you know, A or not A as not A and not A, you know? I cannot, you know, keep doing this kind of reasoning or this kind of arguing over and over again. I don't, by A or not A, I don't mean, you know, start doing that double negation, the thing inside and flipping connectives using the Morgan. This is not what I want to say. And then the intuitionistic logician can say, well, you know, at the end of the day, I mean, it doesn't matter because at the end of the day, you only have one connected, right? I mean, you can derive all the others classically using, for example, Quine's dagger. And the classical logician finally says, no, but this is not true. This is not what I want. This is not what I meant. The fact that we can define one constant or one logical operator from others, it doesn't mean that we have, you know, different operators themselves, right? So this is in the spirit of many works that I've been reading lately. How can you, even if you can define an operator via another, how you can see them in different ways? Marcello already answered this long ago. I mean, you're talking about different things. You're talking about different systems, okay? So this is the idea. And of course, there is the mathematical motivation. This I'm going to pass really quick. So if you have sentences like, for example, this, in the real numbers, if x plus y is 2z, then either x is greater or equal to z or y is greater or equal to z. And then if you put this in intuitionistically, then this is not a theorem at all, because in the real numbers, you cannot, this is a kind of sentence that you cannot decide, you cannot prove constructively. And the classical mathematician is not going to see this because he doesn't understand what the intuitionistic is. But then you can do the thing that I was saying before, you can put a not, you can double negate the whole thing. And then you pass this through these glasses, but then this is going to be really classical. So now the classical mathematician is going to be happy. The intuitionistic mathematician is going to be happy, as we said before. He's going to understand this. This is going to make sense. This is going to be a theorem. Fantastic. But you can do better. So for example, you can say that the implication is intuitionistic. It's constructive completely. Only the disjunction is classical, okay? So then you're going to have people extra happy because, you know, in this way, you can pinpoint exactly where you need to be classical, and the other ones doesn't matter, okay? So this is the idea. And this is something that I've been talking to Alberto, but I'm not going to talk about this in this talk, so I'll skip it. Later on, if you want to discuss something about atoms and how to transform axioms into rules and this kind of things, we can come back to this point, but I'm not going to focus on this. So what I'm going to focus on is exactly to to try to understand what really makes a logical, connected, classical, or intuitionistic. And this is going to include modalities at some point, okay? So it looks huge, but it's not, so don't worry, it's just because I cut the thing in little pieces. And here is the point I'm going to be really quick. So this talk and my whole life, I would say, well, scientific life is about proof theory. This is what I more or less know and what I've been working my whole life. And this the area of mathematical logic whose objects of studies are proofs is called proof theory. So this is what I do. I study proofs, right? And when we talk about proof theoretic semantics, this is what we do. We give meaning to things using proofs and deductions, okay? So this is this, I would say that this is my whole life. So proof theory is all about proofs, right? So the main question that we ask ourselves normally in this area is, when are two proofs equal? And this is a very, very hard question to answer. So this is not the point of this talk. The other thing we can think is, how can we transform a proof into another, or how can we identify patterns and this kind of things. So we're more in the last, the third one of this talk is going to be more on the third one. How can we identify things, or how can we use proofs or proof systems or rules in order to talk about things, okay? Okay, so this is what proof theory does, and you have many applications on that, so I'm not going to talk about any of them. But for example, there are many colleagues attending here the talk that are here that are experts, for example, in taking counter examples from a failed proof search, for example. And there are some other people with whom I work with that do automatic theorem provers and this kind of things. But we're not going to talk about this today. We're going to talk about core things, really core things, basic stuff. So I'll start with the most basic stuff I could do in proof theory. That would be to take the B and the BHK conditions for Brouwer, Kolmogorov, and Heiting, Brouwer, Heiting, and Kolmogorov conditions for intuitionistic logic, and show more or less really quickly how we can read these things using rules, okay? So for example, if you take the first sentence, that would be a proof of A and B is given by presenting a proof of A and a proof of B. This is written this way. So I'm going to say, if I have a proof of A and I have a proof of B, then I have a proof of A and B. And this is known as the introduction rule for conjunction. And this is the representation that we give using figures, rules of this sentence here. And we can do this with all the sentences of BHK sentences. For the disjunction is that A or B, a proof of this is given if I have a proof of A or a proof of B. So then you have these figures here. And the most interesting one is the HT that says that a proof of A implies B is a construction. So you see, construction is already something really intuitionistic, which permits to transform any proof of A into a proof of B. Again, proof transformations and this kind of things, right? So this is represented like this. This A with a bracket means that we are discharging A, the assumption A, in this derivation here. Okay, means that from A, if from A I can prove B, then I can prove A implies B. That'll be exactly in other words, what is written in here. Okay, great. So then you have the elimination rules. This is only introduction rules because they introduce connectives. But then you have the inversion principle that says that everything that you can prove from the premises of something can be proved already from the premises that you have before. And in using this inversion principle, you can formulate elimination rules from the introduction rules. So this is the whole thing. So for example, this is the elimination for the implication, and this is known as modal ponens. Okay, so then you're going to have derivations that are just trees. So for example, this is the derivation of A implies A. And you have, of course, you have things that you have to prove if you want to prove that the system is a good proof system. The first one would be analyticity, that in natural deduction is called normalization. And you have another problems that you want to prove, like, for example, harmony, if the systems are pure or not, etc., etc., etc. Okay, so this is natural deduction in a nutshell, in one slide. If you've never heard about this, but then you have, a very quick course on natural deduction. Then let's pass to sequent calculus. What's sequent calculus? So in natural deduction, what you have is something like this. When I said we have a tree, you have here what you want to prove. You have here many assumptions that you have there. They can be open or closed, doesn't matter. I mean, it means that you're going to have a proof of B from a proof of A1 to a proof of AN. And we represent like this, and this is a tree. Or what sequent systems do is that instead of putting this on the top, this A1 and AN, they carry this hypothesis together with what you want to prove. So now your proofs are going to look like this. So you just move the things that you had here, the assumptions that you had on the top, you put close to with the thing that you want to prove. In the middle, you have a meta level symbol of consequence. Okay, great. Okay, so you have rules, and now we have right and left rules. Good. Then you have derivations, and the problems that you have are not cut elimination. And then if you have cut elimination, then you're going to have a subformula property, and then you can, ask many things about this. Great. Okay, so let's stop the place that I think that you all know. So let's go quick now. So A or not A, okay? For a classical logician, this holds. For an intuitionistic logician, this does not hold always, okay? So why and where do they disagree? So if you take a sequent calculus derivation of both, this is the classical, this is the division in classical logic, it's okay. This is the tentative derivation in intuitionistic logic, you're going to fail. So what Prawitz says is that you're not talking about the same connective. They are not the same connective, okay? Okay, so the classical logician is not asserting what the intuitionistic logician denies. So this is the words of Prawitz, exactly to say that they're not the same. They are not the same connective. Okay, the classical logician asserts A or not E classically, to which the intuitionistic logician does not object. He objects to the universal validity of A or not A intuitionistically, which is not asserted by the classical logician either. So this is the main point. So they are different connectives. They are different ors. Punto y basta. Great. So using this idea for disjunction, what he did was to present a rule system of rules, a natural deduction system, where he is going to have some connectives that are shared between the intuitionistic and the classical logicians, and some are only classical and some are only intuitionistic. This was his choice. We can always say, okay, I don't agree with this, fine, but this was his proposal, and we worked over this proposal, okay? So what is shared for Prawitz? Negation is shared, conjunction is shared, universal quantification is shared. Okay, so these are the rules. They are the normal natural deduction rules that you have for that, introduction ones. I'm just going to put the introduction. Then the classical are going to have his own implication, disjunction, and existential quantifier or quantification, okay? And the rules are like this. So if you are, so this is the point where if you know about natural deduction, then you're going to read this and it's going to make sense to you. So if you want to prove A implies B classically, you have as assumptions up there A and not B, and this is enough. Okay, so this is the interpretation, Prawitz's interpretation for classical implication. Okay, and for the disjunction, you have as assumptions up there the negation of A and the negation of B, and for the existential quantification, you have as assumption for all not A. So you see, the system is not pure because you're defining connectives using negation. And in the case of existential quantification, it's even worse. You're defining the existential quantification based on for all and negation. Okay, so it's not pure. And then you have the intuitionistic rules that are the same that we have for intuitionistic logic, the same thing. So this is Prawitz's the introduction rules for Prawitz's ecumenical system. Okay, cool. So you have harmony now. This is something that for the natural deduction, normal natural deduction that we see in the literature, or Prawitz's one, for example, it's not harmonious. You don't treat the connectives in a harmonic way. And the problem is, of course, double negation. So you don't have double negation, you don't have these things, you have these rules, plus the elimination rules that I'm not going to put here, okay? So this is his proposal. Okay, with Luis, what we did was this was nice, but it has a problem of it's harmonical, but it has a problem of not being pure. So what we did was to make a pure system out of that. What's a pure system? So you're not going to, if you want to define what's going to happen with implication, classical implication, you can only have A, B, not negation anywhere, okay? What's the price to pay? What do you need for doing that? You need an extra context that we call classical context. And this is not new as well. This comes from Girard. So this is a system called a system with stoup, okay? It's a natural deduction system with stoup. So for dealing with the classical connectives, we're going to need the stoup. Instead of putting negations, what we're going to do is everything that we have, we use it to have something negated here. We're just going to store this into the classical context that goes along with the stoup.
It's kind of multi-conclusion natural deduction, right?
Yeah, it's a kind of multi-conclusion natural deduction, more or less, in the sense that the stoup is not multi-conclusion. The stoup has only one formula or none. The multi-conclusion comes in the classical part of the thing. Okay. Yeah, and the idea is the one that I said. I mean, everything that is here in the classical context, you can see as, you know, negated up there in the natural deduction tree. Okay, so this is the idea. Okay, so this is taken from Marcello's paper. A typical proof of the Peirce law. It'll be this one, and he claims it's all ugly, and I agree 100%. Because of this, right? I mean, this is the whole point of the whole problem that you have of the system, natural deduction Prawitz's or Gentzen system for classical logic, that, you know, the double negation formula, and then you have elimination of negation, and then it's a mess, you don't know what's happening, and this is the good. If you go to Marcello's natural deduction, classical natural deduction system, then I'm sorry if I didn't type this. I typed it, but it was not compiling, and I couldn't find the problem. So Luis Carlos had this by hand. Luis, sorry, thank you, and sorry. So this is the proof that Marcello has. So his idea is exactly, I mean, you postpone. It's not really postponing, but you're going to have this the bivalence. You're going to have it on the top of the derivation, and you go from there, right? So this is the idea. And so you have a much simpler proof, right? I mean, what you're doing here, it's completely different. The idea is completely different of this deduction here. It's simpler, and you go to the point, right? Really to the point. That'll be okay. I mean, the double negation should, you should go. They should walk together, right? You shouldn't, hide the things. You go with them and you prove. You use. You need a good system for that, right? Use the system to prove either P or not P up there at the root, okay? But this is not exactly what's going on here in our version. Our version is more related to Dov's Gavai restart rule. And his restart rule is something like this. So you choose something in the middle of the proof that you can, at some point, from there, you can restart with something new, okay? But you justify this at some point. It sounds weird, but it's not. Once you have the stoup, you understand this really well. Well, Bragg has also his out rule that he said it's completely different. For me, it's exactly the same thing. One you read top down, the other you read bottom up, but it's the same thing. And they are all the same thing as the stoup. It's the same thing. What you do in the out and restart is that you're going to hide this A here and choose something else to prove in the place, right? We don't hide. I mean, we hide in the classical context. So this is the only thing we do. We hide this thing here and we go with this thing hidden there, hidden more or less. So it's a mix of classical, it's a mix between classical natural deduction and sequent calculus. It has the same idea as Bragg's and Dov's restart or out is the same thing. You just, you remember something in a way that you want to remember. We prefer to remember it like going with that. And then you use it when you need to use. And that's the thing. The proofs are exactly the same. Here we have contractional weakening. We didn't need to, but for some reasons we decided to put this. And this is an extra rule we have to put, extra premise we have to put in the classical case. But in this case, it's just A implies A here. It'll be the same. So it's a general. It'll be the ecumenical rules. They are a generalization of this natural deduction rules, if you wish. It's the most general way that you can do the thing. Okay, so this is our proof. Is the same as Greg or Dov would have. The only thing is that two things. First, we carry the information with us, and the second and most important one is that we can mix intuitionistic and classical. So this is ecumenical. So I'm talking about peers, right? So that's why I put classical, classical, classical. But I can put intuitionistic, classical. It's going to work. Classical, intuitionistic, classical. It's going to work. Intuitionistic, classical, intuitionistic, classical. It's going to work. If this one is classical, and this is the only one I need to be classical, the other ones, it doesn't matter, okay? And the proof is the same. So, this is, in the sense, we are ecumenical. So this is the thing. We mix classical and intuitionistic logic. Of course, we talk about this, we have to talk about normalization. And you do normalization as the business as always. The only difference is that now you have two contexts. So when you do the composition that you have to do in the strong normalization process, then you have two ways of doing this composition, either in the stoup or in the classical context. So if you have a proof of B from A and you have a proof of A, then you can, glue these two proofs. This is normal stuff. And if you have a proof of B from A and you have a proof of C and A is there being remembered, here you can also glue these two proofs in a nice way. Okay, so it works. The only thing is that you need more. You need more work. So you have a proof of elimination, normalization for that. Okay, so it's okay. It works. So let me pass through really quickly in sequence systems. So you can do the same for sequence systems. So in a work that appeared last year, with Valeria Di Paiva and Luis. We proposed a sequence system for that, a la Prawitz, with negations all over. And this year, we took off the negations, of course, using the stoup. Okay, so we did the same for sequence systems. And what's about proofs and provability in the systems? Doesn't matter if it's classic natural deduction or sequence systems. The thing is that the interpretation of the consequence relation is intuitionistic. This is one thing. So this is provable in natural deduction, sequence calculus, doesn't matter, ecumenical, if and only if the conjunction of the things that you have there implies intuitionistically the thing that you have here. So it's really intrinsically intuitionistic, the consequence relation. But if you have things that are eventually going to become classical at some point, then this turns to classical. So this is really a ecumenical view of consequence relation that you have. And you have conservativity, blah, 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 blah. I'm not going to talk about this, okay? Elimination is non-trivial, completely non-trivial. You have to have notion of polarities, otherwise you're going to collapse to classical logic. Not going to talk about this. Just to tell you that the rules, you have two rules for cut that are admissible. You interleave between both of them when you do cut reductions, and you need polarities. You need to know what the positive and negative formula, classical intuitionistic, blah, blah, blah. But, you know, it works, just it's a lot of work. Okay, so I don't have a clue how I'm in time. Yeah, I have 15 minutes. So I'm going to close this talk talking about modalities, okay? I'm going to give a really fast introduction to modal logic, fast. If you know modal logic, please don't be annoyed. Well, what's about modalities? What a modality is. So in my way of viewing the thing, if you have something like Carlos, tick, 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 handsome, you have many ways of, you know, finishing the sentence, so it makes some sense, right? So for example, is. So then you have a notion of truth, okay? And this is classical logic, for example, is not, is, right? But you can qualify this truth. So you can say Carlos is necessarily handsome or possibly handsome. Then you have an alectic interpretation of modality. So you're qualifying your truth. Is known to be by someone, then you have epistemic interpretation. Is believed to be by someone as well. So you have a doxastic interpretation. Oblige or has the permission or prohibition to be, then you have a deontic interpretation, right? So it's all different ways of qualifying truth, okay? And of course you have now you be, then you have a temporary interpretation. So what you do is you take, for example, Carlos is necessarily handsome. You take this necessarily, that is the qualification of the truth, and you put in the beginning. So now you're going to have a qualification of the truth and something that you know, that you used before, the whole talk up to now, that'll be, well, I was first order in the first part now, propositional. Carlos is handsome. So this is something that we know how to handle. Truth, normal, right? So yeah, so we're going to see, we call the sentence of a P, then necessary P, we represent by box P. We can do the same as possibly, put to the beginning, and then this is done, okay? So this is modal logic in a nutshell. So as I said, we are going to qualify truth. So you can take a truth table. Now, instead of having one fixed truth table, because you're propositional classical logic, what you're going to do is to have words. And you're going to put a proof table in every single words that you have for propositions that you have, atomic propositions. And then you may relate these words or not. A word may be related to itself or not. And that's the thing. So this is the idea of modal logic, okay? So how do you specify this? So how do you do proof theory with that? Well, first of all, well, let me start with modal, because this is the way we're going to, I don't need to pass through this, but this is the way that people understand better. So you can put this into a mathematical structure. You have a set of words, And then you have the relations between these words, and you have a function that's going to assign a truth value to each propositional variable at each word. So this is mathematically what I was saying using drawings, okay? Okay, so then you can, start testing if something is valid or not in that word. For that you have to extend the notion of validity to formulas in general. And about modalities, what you do is you're going to say that something is necessarily true at some word if it is true for every possible word that you see from that part, okay? So then this is box, and this is diamond. Difference between box and diamond is for every word, at least one, there exists one, okay? Okay, and then you can start proving things like in this word, box P is not valid because, in this word here that P sees from W, P is not valid there, and there you go. So you can prove or prove that something is valid or not using only these relations in the validity function in words. Okay, great. So this is the definition. If you know it, okay. If you don't know it, it's not the slide that's going to convince you. It's just a formal way of putting everything that I said up to now. This is classical modal logic. How about constructed modal logic? It's a little bit more complicated. Okay. So in classical modal logic, you have atomic propositions, you have bottom, you have all the propositional connectives that you had before in classical logic, plus the modalities, okay? The thing is that you can define box using diamond and vice versa in classical logic. And the thing is that you only have one axiom at the bottom. At the bottom, at the end of the day, you're talking about this axiom here, that would be the distributivity of the box with respect to the implication, okay? So if you have this grammar, you have this axiom, you have modus ponens and necessitation as rules. Necessitation says that if you prove that something is valid, then box A is valid. Then this logic is going to be represented by that relational system that I just presented to you before. Okay, you have words, you have a relation between them, and that's it. Okay, cool. How about intuitionistic? So this is classical. If you move to intuitionistic, then things are more complicated, because other than the relations, the relation between words, you need a pre-order for talking about the implication, because implication is problematic in intuitionistic logic when you talk about models or semantic interpretation. So you need both of them. So relational structures are not enough. You need bi-relational structures, and for being able to have more or less the same thing. So you have the same axiom, you have the same rules, and you have the same grammar. And you have the same notion. The only thing you need is a closure, restriction here in the semantics, saying that, okay, every time I relate to something, then I go up. I need another word there already that I can go up and then relate. So this is the thing. Cool. Okay. So this, if we only talk about box, this is enough. If we want to talk about diamond as well, then it's a little bit more complicated, because there are many ways of you to put diamonds that they'll be the same in classical logic, but they differ if you're talking constructively. So the first proposal was by Fitch in 48, that he puts this other way of talking about axiom K, now adding the diamonds. And this works fine. Again, you don't need anything. You have the same bi-relational structures, and this is now called constructive modal logic. But then you can talk about, okay, how about distributivity of diamond with respect to disjunction? Then you have these two axioms here that you have to add. Well, this is the zero area of this, but then you need another another closure in your semantics. So now everything makes sense and blah, blah, blah with these two closures here, okay? But then there is this other way of, talking about K as well, that is, they are all independent in intuitionistic modal logic. And when you have all the 5 of them, then you have what's now it's called intuitionistic modal logic, or IK, a la Plotkin and Sterling from 86, okay? So this is the idea. I'm not going to enter into details, just to tell you that this is the modal, this is the model version of intuitionistic modal logic that nowadays we call intuitionistic modal logic. This is the thing. If you go now to figures, so if you move from the semantics to syntax, because this is what I'm going to talk about today, then it's a little bit more complicated. You can for classical logic, you have this modal and classical modal logic. You only need to add this rule here, and you're fine in your sequence system that you had before. Okay. Intuitionistic, if you only have this K here, you only need this rule, and you're fine as well. No difference. If you want theory that we had on the last slide, if you put K3 and K5, then you have to move to what's the name, and multi-conclusion systems, sequence systems, but you're still fine. The problem is that although you're okay then with this 4 axioms here, if you want to prove K4 in the system, you cannot. So it's impossible, okay? You don't have this problem in the modal theory, but you have the problem when you move to the sequence word, okay? Okay, so what do? You do labels. You import the semantics into the syntax, you put labels, and then you're done. So this is the way that Simpson, for example, did or reason when he had his PhD thesis in 94, talking about intuitionistic modal logic. You put labels, okay? So in ecumenical, we can do the same thing. So just to finish, we have the same kind of vision, we adopted the same kind of vision of Simpson, that would be, you take box and diamond and interpret this in first order logics. If your first order logic is classical, you have classical modal logic. If it is intuitionistic, you have intuitionistic modal logic. If it is ecumenical, you have ecumenical modal logic. So the thing is that in ecumenical logic, you have 2 existentials. So you're going to have 2 diamonds. You have 2 diamonds, 1 classical, 1 intuitionistic, and you have 1 box. And this is ecumenical modal logic. You can prove all sorts of things there. So for example, you can prove that if you restrict yourself to classical formulas, then you can have diamond and box, one from the other. But if you are intuitionistic, you cannot. You can mix intuitionistic and classical. And and we have ecumenical birelational structures as well. They're a little bit more complicated than the ones that I showed before, okay? It's just that. So now for you to prove that something is diamond C, or classically possible, you have to do, you have a way to go, okay? I'm not going to enter into details of that. So you have rules for that, not going into details of that as well. You can do the label stuff. You can have these extensions with T, 4, 5, B, whatever. You can have pure systems. So as in the example that I, before that I said that, okay, we took classic Prawitz system with negations, when we turned this into something pure without negations using stoup. We can do the same with label. And we can do more. We can put polarities and we can take off the labels, okay? And so this is something I'm not going to enter into details because this is really technical, and I don't think that this is adequate for talking here. You can take off the labels using nestings, a la fitting, for example. And you can still use stoups and blah, blah, blah. So you have, you know, a very nice and well-behaved system. And you have fragments and extensions, etc. Okay, and for that you need polarities. And this is a little bit more complicated. So to finish, ecumenical systems can help on the agenda of understanding better the connectives and the proof systems. You can mix them. So this is a nice way of saying that we're going to compare them, because we don't have different systems, we have the same system. So we come back to Marcello's argumentation in his paper that, you know, if you have two systems, even if you have the same consequence relation, there are two systems that are talking about two different things. If you have one system, then you're not talking about different things. You're talking about one thing. And you can talk about different things within this one thing. Okay, so this is the whole point, I would say. There are many things we can do with that. So for example, it's nice for you to have a notion where in a proof, a mathematical proof, really mathematical proof, where you are classical, where intuitionistic, without using, you know, double negation everywhere. We can also talk about atoms, and this is something that I said I was going to jump, because, you know, it's a long talk and we're not going to have time. We could talk about other approaches as well. So this is based on Prawitz, but you can have your own, okay? I didn't tell much about constructive ecumenical modal logic. I didn't talk anything about intermediate logics. So for example, constant domains, intuitionistic logic. I didn't talk anything about the algebraic part behind this. And I didn't talk anything about typing. So the algebraic part, there is a student that started doing this right now. We still don't know if there's going to be something new or not, or, you know, anyway. We know that the classical logic is complicated for having categorical interpretation, right? So we don't know if using this we can get rid of this. And typing is something that we started doing, Luis and I as well. And we think that we have a very nice idea of mixing lambda calculus with lambda calculus, for example, or lambda multi-UD calculus and this kind of thing. So, so that's it. Thank you. Grazie mille.
Thank you. Thank you very much.